Pat said, it's a pleasure of ours to host the Hive and all of you. And so welcome to our office. And with that, I will turn it over to Apache.
Thank you. How are you doing? Thank you for being here. My name is Pashu Christensen. I'm the Marketing and Partnerships Manager for the Hive. The Hive think tank has been around for about 16 months, so I hope most of you know about us, but in case you don't, the Hive is a community of data scientists, practitioners, thought leaders, designers, artists, all focused around big data. Thank you for being part of this community. We are over 4,000 members now. Those are our upcoming meetups, and we have many more coming in the South Bay, in San Francisco, and maybe soon on the East Bay as well. We'd like to thank our sponsors, especially Perkins Coie this evening. They've been sponsoring the Hive for 1 year now. It's our 1-year anniversary. So thank you very much. We've had a few events here, I would say 7 or 8 of them. So it's always a pleasure to be here. Thank you. And also, Justin is here from Cloudera for the Edge-based conference, and he's collecting some business cards. We have 2 passes to win tonight, so please make sure to drop your business cards here if you haven't done so before. And at the end of the presentation, we'll have the raffle, and you need to be in the room to collect your prize. So, good luck. And I'm going to hand over the microphone to TM Ravi. He's the founder of the Hive. Thank you.
Thank you, Pashu. Thank you guys for being here. First, I'd like to thank Perkins Coie for hosting us. There's a whole bunch of you who are in early stage startups or entrepreneurs who want to do a startup. And so Perkins Coie is a great law firm to help you structure your company, to make sure you have your intellectual property sort of covered and protected. So please reach out to the Perkins Coie people here. Just brief, a number of you asked me what's the Hive. So Hive is a fund. We invest in early stage companies, all with a common theme, which is they're all around data. And more especially, we tend to focus on data-driven applications. Some of our, I see, so you met Pashu, who takes care of the Hive think tank. Some of our team members are here today, myself, Lance Riddell is there. So uniquely for fund, we have some technology people who work closely with our entrepreneurs to support their companies. We have some people on the business side. We have some people on the vertical side. So Craig is a founder of a company called Rubicon that just went public on last Tuesday. Stock went up by 34%, and our other founder was the guy who incubated the company, funded it, is on the board, they are the largest shareholders. So Rubicon is a good example of the kind of companies the Hive does, which is, this is a data-driven company, it's a real-time bidding platform, uses Hadoop, uses a bunch of data science, and where we have been able to work with them from the very beginning. Our focus is on largely on applications in different line of business processes or different verticals. So if you're an entrepreneur with a lot of domain experience in this space, we'd love to meet with you. We are hiring, we are looking for specialists as entrepreneur in residence, in security, in fraud detection, Internet of Things. So surprise, surprise, we are interested in creating companies in this space. We are always looking for senior engineers in Hadoop, in Spark. So the Databricks guys, if you're thinking of moving. I'm very pleased to welcome the folks from Spark. There was a day when basically Hadoop was MapReduce plus HDFS, and MapReduce was the only way to do things. And so today you see even the Hadoop framework has morphed to support other things other than MapReduce. And so both the gentlemen today are co-founders of Databricks. They're both committers to Spark. They both came from the AMP Labs project. And so please join the conversation, tweet with hashtag HypeData, and join us on Facebook. And with that, I'd like to welcome, there you are, Raymond, and I don't know the order that...
I'll do it first, yeah.
Okay, and you have your mic, so I think you're all set.
This working? Okay, excellent.
So we'll have a presentation, and then if you can hold your questions to the end.
Is that a collector? Thanks for the introduction, and thanks for inviting us to speak here. It's very exciting to meet all of you guys. Before I start, can I get a show of hands? How many of you are engineers? I see. Now, how many of you actually write code? I see a couple guys put down their hands now. Anyway, so I tried to make this talk so slightly more introductory, so even if you don't write code, you can get something out of it by why are people using Spark, and maybe why you should get the people writing code for you to use Spark. And my name is Renaud, and I'm one of the co-founders of Databricks, and as well as a core member of the Spark open source community. And my colleague here, Patrick, also another co-founder of Databricks, coming back and give the talk. And so we separated the talk into two parts today. The first part is I myself will give an introduction to Spark, Apache Spark, and then Patrick will talk about beyond the Spark core, which means covers a lot of the different higher level components on top of Spark. And unfortunately, if you read the event description really carefully, as most people typically do, you realize the third speaker that unfortunately can't make it today. He's the guy that knows a lot more about machine learning than both of us. So if you have like math problems, maybe just send me an email and I'll forward it to you. So before Spark, can I get another show of hands? How many people know about Hadoop? And do you know what it is? Have you ever written a Hadoop job? Right. Half of the people put up their hands. And how many of you have heard about Spark before today? Why are we giving this talk? How many of you have written a Spark job before? Okay, good. All right, now let's do a purpose. Okay, so what's good about Hadoop? What Hadoop really does well is to transform and commoditize storage. It makes it much cheaper to store a large amount of data across a cluster of commodity machines. This means you almost never have to delete data anymore. And now you don't have to worry about sort of freshness, you just dump the data in. You don't have to worry too much about schema, you don't have to worry about how to use it in the future. You can just put it in and worry about those problems in the future. But what really Hadoop struggles is, from the beginning, there's sort of one computation paradigm called MapReduce, which forces everybody to think in terms of a strict two-phase logic of map and reduce. While it does what it was designed originally for very well, web crawling very well, but it doesn't actually suit a lot of other type of data analysis tasks. For example, it is kind of clunky. It's a little bit slow, because if you want to run stuff in an interactive fashion, it's actually really hard to accomplish that and to do MapReduce. And if you want to write complex jobs, typically you have to chain a series of MapReduce jobs together, which leaves us a little bit unintuitive for developers. And now with that, let me introduce you to Spark. So one definition of Spark, which I just rolled up today, you probably can't find it anywhere else online yet, is just a cluster compute engine that can work with a variety of workloads very well. So Spark can work with ETLs. You can use Spark to do machine learning. You can use Spark to do graph processing. And you can use Spark to run SQL-like queries. And what this means is you can actually now use a single system to cover a wide range of workloads. And you don't have to manage anymore multiple different things running different consolidate all of them. Your developers learn one thing, one programming API, and your ops people only have to manage one thing and install it. And the sort of to walk through some high-level benefits of Spark is, I think there's 4 points. The first part is it's really fast. That's why typically what people come to Spark first, when what they were looking for, because it's a lot faster. When you express something in Spark, the similar application written in Spark is typically can outperform the MapReduce counterparts by a large factor. Sometimes an order of magnitude, sometimes 2 orders of magnitude, depending on workload. And the other one is it provides a lot of sophistication. You could run a lot of very complicated algorithms, such as machine learning, graph computation. You could run streaming, all of them in the same package. And it's actually much easier to use, which is equally, I think, as important and often overlooked, which is developers' productivity. Often when you rewrite an application that was originally written for Hadoop MapReduce and you rewrite it against Spark, it gets a hell lot shorter. And what is shorter is the short conciseness value. It means the program shorter, it's easier to understand, it's easier to test, it's easier to reason about, which increases your developer productivity. And there's high-level programming APIs exposed for both Scala, Python, and Java. So it means you're not confined to using a single Java API, but you can actually use a set of different languages, and they just work out of the box. And we also sort of make Spark work by integrating with the existing interactive shell, the way it might otherwise known as REPL, in both Python and Scala. So you actually, the programmers can, or data analysis, data scientists, you can actually analyze data directly interactive in the shell without even the need to compile a program to run it. And this works against the real cluster too. And it goes beyond what MapReduce could do, which is MapReduce. It provides over 80 high-level operators. For example, operators such as join, filter, and all of this. And now you don't have to shoehorn sort of a developer's mindset into MapReduces. There's a lot of operators supported right out of the box. And best of all, you can now use a single language just across a different suite of workflows. And the last but not least, this part just surprised me, this chart. The Spark in the past 6 months has become the most active big data open source framework in terms of number of contributors. So for the past year, as of February 2014, it's over 120 contributors that contributed code to the Apache Spark project. And that number actually went up to, I think, close to 170 now, just in the mere 2 months short time frame. So now let's dive a little bit into each of the subpoints, right? First is easy. What does easy actually mean? I told you, I promised it was shorter, it's more concise. But let's go into the details. So first of all, it's easy to set up. A lot of you probably run MapReduce jobs before, and when you first try to learn MapReduce, you would usually think, let's download it to my local laptop and try running, right? And then you realize it's actually not a single command you could run directly out of the box. It's like this, requires some configuration. So for Spark, you could actually just download Spark, get the tarball, untar it, and then start running the interactive shell directly out of the box without any configurations on your laptop. And then you can start developing programs using both the Python, Scala, and the Java API. And as you develop them, and as you need to sort of finish testing your programs locally and you want to scale it out, you can just roll it out on Apache Hadoop Yarn or on Apache Mesos, or even deploy it without any of the Hadoop support on the cluster. And the whole thing, the same sort of set of workflows still works when you go from a local mode to the whole cluster mode. Just to show you some APIs here, I'll go a little bit more into details toward the end of the talk. And the other one is just APIs. So in Spark, you can sort of forget about MapReduce. MapReduce is no longer the core concept. The core concept is distributed data sets. So essentially, we have this thing called RDD. The core programming concept in Spark is RDDs, resilient distributed data sets. And think of RDD as just logically a collection of records that's partitioned and distributed across the cluster. And you can build RDDs by applying transformations on RDDs, on other RDDs. or you can build RDBs by pointing Spark to an existing external data set and external storage, for example, HDFS. And RDBs are fault tolerant. So when we talk about distributed systems, when we talk about large clusters and big data, nodes could fail anytime when you're running your jobs. And Spark actually takes care of that because the RDB abstraction itself is fault tolerant. If a node goes down, the data that resides on that node gets automatically recomputed on other nodes. And given distributed data sets, what can you do with them? You could operate on them. There's two kinds of operators. There's transformations, there's actions. Transformations essentially create new RDBs from sort of existing RDBs. And MapReduce is a typical transformation. There's a lot more to that, and we'll show you a slide later. And the other kind of operation is actions. So actions are the kind of operation that they usually actually want some operations to happen. For example, count is one action that usually requires an integer to come back from a programming API. And save is another example where when a user calls save, you better save the data somewhere on some external storage format. So when we talk about this over 80 operators, what are they, right? It starts to cover. So first we got our base cover, this MapReduce. But on top of MapReduce, you think about your typical data pipeline. Usually you have to join multiple data sources together. Sometimes you might sample your data set to get sort of a small set of data so you can play with very quickly. And sometimes maybe you want to run aggregations. So almost all of them are just supported out of the box in Spark. You very rarely need to like write a new operator yourself. Usually it works very well just by composing a sequence of simple operators. And now, so one thing we mentioned earlier was Spark programs tend to be a lot shorter than the Hadoop MapReduce programs. So this is one example of this. How many of you know word count? Okay, all right, about half. So word count is sort of self-evident. It just counts how many times each word appears. I don't know why, but when you talk about Hadoop MapReduce, and you talk about big data, everybody loves counting words. As if that's the most important thing you ever do with your data, which is probably true. So word count, if you go to any sort of big data example, it's usually the first one they show you. This is like the hello world of big data, right? And this is sort of how you run word count in Hadoop MapReduce. Now, obviously it's really hard to read. This is kind of, the text is kind of small, but don't worry about it. But so basically I'm just showing you a side-by-side contrast. If you implement word count in Spark, that's the length you get using a Scala API. And if you're writing, and this is the length you would get if you're writing the Hadoop MapReduce API. And now Scala is naturally a slightly more a concise language than Java. If you write this in Java, it will be slightly longer, but not by much. And part of it is because thanks to all these high-level APIs, it's sort of well-designed and matches better your typical data work. And the second point we talked about was fast. That's why a lot of people sort of come to Spark in the first place. And why Spark faster? I got asked this question a lot. There's actually, I think, two important parts. The first part is this in-memory caching. So in Spark, you could do in-memory computation out of the box. This means you could put RDBs actually in memory, make them resident in memory. And then we all know from our computer science 101 that memories are faster than this. So when you run your workloads against data in memory, it typically ends up a lot faster. But there's more to that. The second part, which I think is equally important, even sometimes more important, is because Spark supports a general execution graph. It supports a lot of higher level operators. Often you don't need to sort of limit your workflow and express them in MapReduce. Now you can express them in a wide variety of high level operators. That leaves more room for optimizations. So Spark scheduler and the engine itself has more room because it knows, for example, you're joining two data sources together. There's a certain way it can schedule these jobs. For example, if you're doing aggregations and if your data is already partitioned, maybe I don't need to shuffle the data. This is the nerd part of the talk. So when you combine these two, what you get is something like this. So these are realistic examples of running machine learning algorithms And in here, the data is fit in memory on the cluster for both k-means and longitudinal regression. And in the case of LR, because this is a computationally very light workload, it's actually like almost 2 orders of magnitude faster than MapReduce. And in the case of k-means, it's slightly more computationally intensive. And Spark is still over an order of magnitude faster. And so, so this is actually one of the main reasons why Spark is becoming the de facto standard for running distributed machine learning, both in the Hadoop ecosystem and outside of the Hadoop ecosystem. Because of, in the case of machine learning, the same memory caching and sort of high-level operator graph really helps with the work. Now, let me go into the more engineering part of this. I show you benefits, I show you high-level abstractions. Now, how do I actually work with it? So again, this is a recap. The core programming concept, programming abstraction in Spark, is called RDBs. And how many of you remember what RD stands for? Not bad. I could barely remember that myself. So the core concepts are RDBs. And there's 2 ways of creating RDBs. The first way is just pointing it out to some external storage. For example, a set of files on HDFS. So this is one example right there. SC in this case is a Spark context, which is similar to a MapReduce job context. Another way is by applying transformations on RDBs. And transformations are what we call basic coarse grain transformation, where you give it a function and you call one of the operators, and then you create your new RDB. In this case, for example, filter would be one transformation, which is also just a high-level operator. And in this case, I'm sort of passing this is the Python syntax, and lambda is an anonymous function. So in this case, what it's doing is for each of the line in the text file, I'm going to run this lambda function. If the lambda function returns true, I keep the data in the data set, in the lines with Spark RDB. If it's not true, we throw that out. And in here, it's essentially checking if the line contains Spark. So this transformations, which creates new RDB. And then there's actions. Actions typically return a value or sort of changes some state of external storage. So for example, you want to run a count to count how many times Spark appears in this text file. This is how you would do it. Just run a count. The program is going to return counts as a normal programming function. It's going to return you the number of times it satisfies the filter. And there's a lot of other options, actions you could look it up online. For example, first take a sort of like the limit in SQL, which returns you the first 10 elements in something. And there's also save. You can save to Hadoop. You can save to HBase. So now, still very abstract. Let's walk through an example and walk through the execution of the whole thing. There's an example of log mining. So let's say I have a bunch of logs stored on HDFS, and now my production system is going wrong. I'm sort of random data scientist got put in by the ops guy. Please, Spark, help me. And let's say I don't have Splunk installed yet. So in this case, we have Spark. Again, this is just a Spark context. It's a normal variable, and I think in this case we're using the Python programming language, Python API. So we have we just point using a text file operator on the Spark context, point Spark to a set of files on HDFS. That creates a new RDB called lines. And lines will be. And now let's say we're only interested in errors. We want to find just all the errors from the logs we have. So you do this actually just easily by applying the filter function to create a new RDB called error. And again, you pass filter a lambda function, an anonymous function. What this does is for each line, it's going to look at whether the line starts with error or not. So it's just standard Python. It's a Python function start. It's on strings. And now we transform. Essentially, we create a transformation. We have a transform after. And then let's say my lines are tab separated, and maybe the first token is always error or info or warning, and the second token is just a time. And I'm only interested in the third token, which is actually the error message. So now it's very easy. You apply, now going back to MapReduce, you apply a map. And what map does is map applies this anonymous function to every element in the errors RDB. So essentially for every line in errors, you're going to split it. This is just string split in Python by tab. And then you found the third element, zero index, the third element, and then put them back into a messages. So now you created these messages, which essentially is a distributed collection that contains a set of messages in the cluster. So next is, let's say if I know I'm going to repeatedly query the set of messages because the first time I'm going to run a job, I might not found a prompt. I'm not that lucky, I can do it the second time, or maybe even the third or fourth. You can actually tell Spark that this data set is going to be repeatedly accessed. Let's put them in memory. So it caches like a hint to Spark. And up until this point, I might have sort of given you the impression that the cluster is very busy, the cluster is loading all the data from HDFS, the cluster is now doing filtering, string splits, and all that. But actually, up until this point, nothing really happens on the cluster. All this work is just building out metadata on the application itself. So what this does is really just tells the application at Spark that lines can be computed by pointing to some file on HDFS. And errors can be computed by applying a filter on lines. And messages can be computed by applying a map on errors. So we build up all this metadata, or we call lineage in Spark, if you're curious. We build up this metadata in Spark, but we hasn't really done any real work. Now let's say I want to actually see how many times MySQL appears my error log. The way we do this, you just apply a filter to create the RDB. This time we're not really naming the RDB in a variable, we're just creating a new RDB, and we count how many elements are in that RDB. So remember, count is an action. What this means is the user wants an integer back. It wants how many times so MySQL appears. So because count is an action, now the Spark application is going to talk to the Spark scheduler and start actually launching jobs. So first, the application is going to query the HDFS name node because we know in the beginning, all our data points to somewhere, some data on HDFS. It's going to query the name node to find out how many blocks my files have and where they are. And then the driver is actually, the application driver is going to launch programs, launch tasks, and send them to the workers to be executed. So in this case, it's going to, each of the workers is going to read the blocks from HDFS, and it's going to process them. And because we told Spark want to actually catch the messages RDB, for each of the blocks that computed for messages, the worker is going to put them in memory, put them resident in memory on each of the workers. And then the worker is going to return the results back to the master. And in this case, each of them is going to return one integer, and the master does the final aggregation, how many times each integer appears. And let's say now the MySQL wasn't, you figure out maybe MySQL is fine, you didn't find any errors. Let's see like PHP, a live website. How many times did PHP appear? And this time, because the data is already in memory, the driver is going to send the task to the workers, and the worker is going to read directly from the cache copy of the data in memory. And they're going to return the data in much faster, because now you're just reading from memory instead of reading from disk. And sometimes this really sort of changed the interactivity of jobs. For example, in one case, we were just dumping the entire Wikipedia in memory so on HDFS, and we started doing distributed graph on Wikipedia. If you on like 20 EC2 machines, if it's I can send you guys the slides, but don't worry. If the whole data set's on disk, it takes over 20 seconds usually to just grab through like 60 gigabytes of data. And if it's in memory, you can actually do it in less than a second. And so really, when you combine this in-memory caching and high-level operators, you can compose much more powerful applications in a much simpler, much faster. And so before I wrap up my talk and give it to Patrick, really just to summarize my talk, there's 4 bullet points for Spark. First is high performance. You can get to your data and get value out of them faster. Which equally important is higher developer productivity. So it makes developers' life and whoever works for you life easier. And you can run using Spark some of the most advanced algorithms today. And this wide, vibrant open source community for Spark. Now, I'm going to pass the mic over to Patrick.
Thank you, Ronald. I need to get my slide. Give Ronald a round of applause. Oh, wait,
Okay.
Yep, I just need to open my slides.
Yeah.
Would you mind just full
Sure.
screen? Hi, everyone. Thanks a lot for being here. So I'll talk for maybe another 20 minutes or so, and we'll try to leave plenty of time for questions. What's that? Oh, yeah. So I'm Patrick Wendell. About me, I'm a committer and TMC member on Spark. I'm also the release manager for our 1.0 release, which is a huge release that we're right in the middle of working on as a part of the Spark project. I was on my way to getting a PhD at Berkeley, and my advisor, Jan, left to co-found this company, Databricks, so I left with him with a master's degree. They finished someday, not sure.
Never know what happened.
Yeah, he's skeptical that I'm going to finish. Okay, so now I'm mostly working on open source stuff at Databricks, and my research focus was always on kind of operating systems and networking, so that's kind of where my expertise lies. Reynolds stole my show of hands, so I'm not going to do this. Although I will ask, one thing Reynolds didn't ask, which I think is something no one should be ashamed to raise their hand for, is number 2 here. How many people here are in a sales or marketing or business development kind of role? Okay, so there's maybe a fifth of the crowd or so is wearing that hat, and that's definitely a group we'll try to accommodate in our talks. Okay, so I'm going to skip this. So I'm going to give just a couple high-level thoughts, and then I'll talk more specifically about the higher-level libraries that are sitting on top of Spark, which are increasingly the area of interest both for the development inside of the project and what's bringing many new users to Spark today. So the dirty secret of data analytics is that in modern environments, what most developers spend a lot of their time doing is kind of fighting sort of hard to configure or use systems, poor APIs, broken types of software. And this is something that is keeping people from doing their job and from actually doing productive data analysis. And a lot of machine time is spent doing things that also can be avoided, like moving data between different types of systems. There's a huge fragmentation in what types of application frameworks people use, and as a result, there's tons of time spent just converting and moving data between these systems. These are some low-hanging fruits that Spark is trying to address in kind of the broader trends of inefficiencies in the data management landscape. So what is kind of our project philosophy in Spark? Well, we're really trying to make life easy and productive for data scientists. So we're trying to find these inefficiencies and get rid of them. What does that mean? It means that we focus on sort of really well-documented and expressive APIs. We want to have powerful domain-specific libraries. So when people are focusing on higher-level problems in certain areas, we want to be able to facilitate them, give them a library that they can use. Easy integration with other storage systems. And lastly, we have all these performance optimizations like caching and other things that can avoid data movement between jobs. And we also kind of try to be developer-friendly in the way we run the project overall. One thing Reynolds alluded to before is we are very open to external patches. We will always look at them and review them, and very often we'll merge them into Spark. We're happy to accept work from outside of the community, not only just bug fixes, but like features and things that are useful to people. And we do regular maintenance releases. So we actually do sort of minor stability releases so people can upgrade and get only bug fixes and not have to worry about potentially unstable new features. This is kind of just a software engineering one-on-one thing, but a lot of the Hadoop ecosystems projects don't do this. They don't take the time to go and make bug fix releases for people, and as a result, the downstream consumers of those pieces of software have to choose if they want to stay on the version they're on now or upgrade to get some bug fixes, but potentially have a bunch of new bugs that they didn't know about. So what I'm talking about today is not the core sort of Spark API that Reynolds alluded to, but it's what's going on in the ecosystem now, which is a bunch of higher level frameworks that are currently being developed on top of the core Spark API. And what's something that is cool and was not maybe totally obvious and intuitive at the beginning of the Spark project several years ago is that this API of this very simple API of I have distributed collections, and I want to do just some basic types of operations on them. I want to sort of transform and map them and filter and group by and maybe persist them in memory. These fairly low-level operators turned out to be sufficiently general and powerful to allow a ton of different high-level programming models, which is not like an obvious thing that would be the case, but over time we've seen that this actually turned out to be a very powerful abstraction for doing many different kinds of computation. And so with this RDD abstraction has been extended in a number of ways. Today I'm going to go over each of the higher level libraries just in a kind of a introductory and overview fashion, but there's a lot to dig into in each of these cases. So this core RDD abstraction has been extended. So you have Spark streaming, which looks at sort of real-time streams viewed as a sequence of RDDs. So a sort of micro-batch model that we'll talk about, where you have new RDDs in each time interval every second or every 30 seconds or 15 seconds. You have Spark SQL, which is imposing schemas on top of RDDs and then allowing you to do to write computation on these RDDs using SQL, so doing selects and group bys and filters in a SQL dialect, which I'll show. And there's MLlib, which allows you to specify matrix in terms of an RDD and do things like linear regression and k-means clustering and various types of mathematical algorithms on top of these. And finally, GraphX is also a numerical sort of